Good morning, everyone. What we're looking at today is lesson 1.8 in this unit, which deals with what's called relative motion or navigation. And your book should be open to page 35 of the unit handout. We're going to be solving problems today where the motion of an object is determined or influenced by multiple sources. So, for example, a plane flying through the air, how it actually moves is a result of which way it points and the engine thrust that the plane provides, and it's also determined by which way the wind is blowing and the velocity of that. When you have a boat going across a river, the velocity that the boat is able to move through water determines which way the boat will move, but the direction that the water is flowing in the river also affects which way the boat will move. And that's what we mean by multiple sources. And really what this is going to boil down to is we're going to have multiple vectors that are velocity vectors that need to be combined together. We also have to, in general, understand motion as having two components. So when you have an object moving in some direction, there is a horizontal motion and there is a vertical motion that happen at the same time. Now, before we get to the formal lesson, I have an analogy here, and this analogy is not in your note package. It's something that I thought of to add afterwards to the beginning of this video. And hopefully, once you look at it, you'll understand the content in the lesson a lot better. All right, this says that we have a small bug walking with a speed of 7 centimeters per second. And I'm telling you that it's going to start walking from one end of a mechanical walkway at an airport. So the mechanical walkway is a moving sidewalk, basically it's sometimes called. Some other information that I'm giving you, the walkway is 9.9 meters long. And for some particular reason, there's a fault in the engine that's driving the belt on this thing. It's only moving at a very, very slow rate of 2 centimeters per second. So there's a diagram showing what's going to happen here and summarizing all of the information. And the question is this. The question is, how long would it take the bug to reach the other end of the walkway? Well, if the walkway were not moving, then the bug would be traveling 7 centimeters every second. And I know it sounds like I'm just repeating that speed, but I'm talking here in English about what that means. The bug travels 7 centimeters every second. So every second that goes by, that bug will move 7 centimeters to the right. But it's doing so on a walkway that's moving 2 centimeters to the right. Now the bug is not very intelligent. As far as the bug is concerned, it is still walking with a speed of 7 centimeters per second. But if we're standing outside watching this happen, the bug moves at 7 centimeters per second, and the walkway is adding another 2 centimeters per second to it. And I want you to notice something here. And I think it's very important because it ties it nicely together with what we learned over the past couple of days. That this is a velocity of, we'll just say the bug, this is a velocity of the walkway, and the velocity that actually results is going to be equal to the 7 centimeters per second plus the 2 centimeters per second. Well, that means it's equal to the sum of those two velocities. And those two velocities that I have on the right, let me highlight them for you. These two velocities of 7 centimeters per second to the right and 2 centimeters per second to the right are vectors. So how is it that you add vectors together if they're in the same direction? The answer is you add the magnitudes together. So that means that the velocity that actually results, and I'm going to continue to use, everybody, that concept of the total vectors being what we call the resultant vector or the resulting vector. will be equal to 7 centimeters per second plus 2 centimeters per second, which means what the bug really does, resultant means what really happens, is it moves at 9 centimeters per second. And it's a pretty simple matter now to use speed equals distance over time. To put in the 9 centimeters per second, I'm going to leave the units out. To put in the 9 centimeters per second, to put in the 990 centimeters over the time, and everybody should be comfortable with solving that little equation for t. T will be equal to 990 divided by 9, and the answer to this question is then 990 divided by 9 is 110 seconds. So it's going to take the bug 110 seconds to reach the end of the walkway. And that's not in your notes. It's just something that I want us to think about. Now, let's stop for a second and think a little bit further. Okay, later on in the day, the bug heads back home. I don't know what the bug was doing at the airport all day, but now it's time to go home, so the bug gets back on the walkway, but it travels to the left. Now, if it travels at 7 centimeters per second, that means, and again, I'm not just repeating the velocity, I'm explaining what that means. It means that if you wait 1 second, the bug will have traveled 7 centimeters to the left. But in that 1 second, the walkway will have moved 2 centimeters to the right, which means even though the bug is walking 7 centimeters per second, the bug will only actually be moving to the left at 5 centimeters per second. And everybody, we get to the same idea that I talked about earlier, that the resultant velocity is going to be equal to the velocity of the bug plus the velocity of the walkway. Except now we have velocities in opposite directions that we're adding together. So we've learned that when you take this vector that's in one direction and this vector that's in the opposite direction, that you take the larger minus the smaller, and in this case we get 5 centimeters per second, and the direction of that would be to the left. And now if we want to find out how long it's going to take the bug to get back home, we can use speed equals distance over time again. This time the speed is going to be a lowly 5 centimeters per second, and that will be equal to 990 centimeters over the time. And again, I think it's pretty straightforward for everybody to be able to solve that for t. You're going to take 990 divided by 5, which I believe is going to give you 198, but my brain is certainly not operating on all cylinders right now, so I'm going to check that out. 990 divided by 5, yep, 198 seconds. And now we're going to have a totally different question with Mr. Bug here. The next day the bug decides to travel across the walkway. And the bug is traveling towards the bottom of the screen here at 7 centimeters per second, and the walkway is 140 centimeters wide. So I have added, everybody, this piece of information. And the question is, how long does it take the bug to reach the other side? Well, the bug doesn't know that the walkway is moving to the right. The bottom line is the bug is going to move at 7 centimeters per second, and this displacement is 140 centimeters, so we can simply use those two quantities. Speed equals distance over time, so we can take the 7 centimeters per second, and we can set that equal to 140 centimeters over the time. Solve that for the time, and you're going to get 20 seconds. So you're going to really have to think carefully about this. If the walkway wasn't moving and the bug decided to take this little journey from one side to the other, it would take 20 seconds. If the walkway was moving slowly to the right, it's still going to take the bug 20 seconds to get to the other side. If the walkway was moving very fast to the right, it's still going to take the bug 20 seconds to move across the walkway. Now there's another question here I'm asking us to think about, which is where will the bug be when it reaches the other side? So the bug is going to reach the other side here, but in that 20 seconds, the walkway's been moving to the right. So in that whole 20 seconds, the walkway has been moving to the right with a speed of 2 centimeters per second. That means the bug will now be moved to the right. And it isn't that the bug moved from where it is in the diagram to this place and then moved this way. It's happening at the same time. But we can use speed equals distance over time. You can put in the speed of 2 centimeters per second, put in the time of 20 seconds, and solving this for d is pretty easy. You're going to get 40 centimeters. So the answer is the bug will be 40 centimeters to the right of where it started. And the thing I want to point out to everybody before we get formally started with the lesson, and this is the most important aspect of this little warm-up that I've made for you, is the following. When we did this calculation, that speed was a vertical speed and that displacement was a vertical displacement. When we did this calculation, we were finding a horizontal displacement and we were using a horizontal speed. And that's maybe the biggest lesson out of all of this, is that if you have two-dimensional motion, you can use speed equals distance over time, but you have to use it with y components or with x components. All right, now we can get started with the examples. Example 1 says a boat with an engine speed of 4 meters per second is in a river that is flowing west at 3 meters per second. Now, I want to make sure before we get started here you understand what I mean by an engine speed. If I tell you that the engine speed of a boat is 4 meters per second, what I'm saying is if you dumped that boat into a lake where the water wasn't moving, it's capable of moving through the water at 4 meters per second. This is like the bug's speed of 7 centimeters per second. So what would the resultant velocity of the boat be if the boat pointed west? So the resultant velocity of the boat, we always put resultant, will be equal to the velocity that the boat has in still water plus the velocity of the water. And, when you take a look at that red equation that you're writing down right now, you don't really need that. To many of us, I think it would be common sense that if the river is flowing west at 3 meters per second and the boat is traveling west at 4 meters per second, then what's going to happen is it's going to actually be traveling at the sum of those two numbers. But that's what we've got here. The velocity of the boat in still water is 4 meters per second, and it's pointed west, plus the velocity of the water, while the river is flowing at 3 meters per second, and it's flowing west, which means that the resultant velocity of the boat is 7 meters per second west. What if the boat is pointing east? Well, we still use this same thing, and I don't know. You can write it down again if you like. You don't have to. The resultant velocity is still the velocity of the boat plus the velocity of the water, except now we're taking 4 meters per second east, and we are adding 3 meters per second west, which is only going to give us 1 meter per second east. So this idea here this formula is what you would use to find the resultant velocity of the boat in any situation. You take the velocity of the boat and you add the velocity of the water. It's just that how you find the answer depends on the direction of the velocity of the water. Okay, what if the boat heads north? Well, let me summarize for you here that the velocity of the water was 3 meters per second west. I better just go back and double check that. Yep. And the velocity of the boat is 4 meters per second, and in part C it's heading north. So how do we add these two vectors? Well, you've spent some time over the past couple of days practicing this. Since these are perpendicular to each other, you draw them tip to tail. I would personally draw the horizontal first, and then we can draw the vertical. So what do we have in our diagram? We have 4 meters per second vertically, 3 meters per second horizontally, and the sum of those will be the velocity that results. This is the resultant velocity. So you need to find that, and you need to find the angle and write the angle as north of west. I'm going to give everybody 20 seconds or so to run those calculations through your calculator while I do it. Well, you're going to get 5. I know this Pythagorean triangle gives us 3, 4, 5 for the hypotenuse. But you would take 3 squared plus 4 squared. Then you would take the square root and you get 5 to find the angle. Make sure you're in degrees. Inverse tan of opposite over adjacent gives me 53 degrees. So the answer to this question in C is 5 meters per second at an angle of 53 degrees north of west. All right, I would like to explain to you now what that really means, having these two perpendicular velocities. So there's a picture showing what's going on. The boat that you're seeing at the bottom of this picture on your screen is at the beginning of its journey. It's just turned the key on the ignition. It's fired the engines on the boat so that it's going to be going towards the north at 4 meters per second. Well, it's not actually going to travel north, though. We know that. What's going to happen is it's going to travel at an angle. And it's going to be traveling along that line at 5 meters per second. But what the boat is doing as it travels 5 meters per second along that blue line is it's doing two things. It's moving north at 4 meters per second, and it's moving west at 3 meters per second. So every second that goes by, the boat will be 4 meters closer to the shore, and it will be 3 meters further downstream. Let me show you that visually. If you look at the bottom of your screen, it says t equals 0 seconds. If we wait 1 second and take a snapshot of where the boat is, the boat will be in that location. And the fact of the matter is the boat will still be pointing north. The boat will not turn and twist in the direction of the blue line. If we wait another second and we look at t equals 2 seconds in total, it would have traveled another 4 meters towards the top of the screen and another 3 meters towards the left. And that action continues. And again, I want to summarize this by telling you what I've already told you, which is that it is moving at a constant speed, which means speed equals distance over time. I think I'm going to move that just so you can see it a little better. And you were allowed to use that speed equals distance over time in your calculations as long as you use a horizontal velocity and a horizontal distance, or a vertical velocity and a vertical distance. So those components or those motions are what we say in physics, they are independent of each other. It doesn't matter how fast the river's flowing, if the boat pushes north at 4 meters per second, that's what it will do. All right, number 2. A motorboat with an engine speed of 20 meters per second heads east. So this is what I would call the velocity of the boat. It's 20 meters per second east. When I say the velocity of the boat, I mean the velocity of the boat if it were in still water, if it were sitting in a lake moving through the lake water, but not in a flowing river. We're also told that the velocity of the water, you could use R for river, I'm using W for water, is 5 meters per second north. The river is 80 meters wide. So just a second here. I want to be very careful about that 80 meters. When I write down D equals 80 meters, since that's 80 meters, think about this, the river is flowing north. If we draw a little diagram, the river is flowing this way. If I'm told that the river is 80 meters wide, that's a displacement that's east. The boat starts here and moves to the east across the river. So that 80 meters is a displacement east. Let's keep that in mind. Now let's answer part A of the question. What is the resultant velocity of the boat? Well, that's pretty easy. We have to add these two vectors together, and we add them together by drawing them tip to tail. So I can draw 20 meters per second east, followed by 5 meters per second north. And we're back, everybody, to that really basic calculation that you've seen so often over the past few days. We want to find the hypotenuse of that and the angle. This will be the resultant velocity. All right, so 20 squared plus 5 squared, take the square root. 21, we're going to round it to 21 meters per second. If you wrote 20.6, that's fine. The angle is the inverse tan of opposite over adjacent. My mistake, let me do that again. The opposite over adjacent, inverse tan, about 14 degrees north of east. So my answer, I'll just put it in blue. My answer is that the resultant velocity is 21 meters per second at an angle of 14 degrees north of east. Take a look at B. How long does it take the boat to cross the river? Okay, wait. Crossing the river is 80 meters wide. But again, we've said that that translates to a displacement for the boat of 80 meters east. So when you start looking at your speed equals distance over time formula to solve this problem, to find the time, we have to use 80 meters east, and that means we have to use a velocity east. You can use that speed equals distance over time formula for any situation as long as the direction of the displacement and the direction of the velocity are the same. If you want to be very technical, I should put vector symbols there. But if I go back and look at the speed of the boat, which is the east velocity, that's 20 meters per second. So I'm going to put the 20 in for the velocity. I'm going to put the 80 in for the displacement. And I'm going to solve for t. I'll give everybody just a minute to write that down and calculate what you get for t. You're going to cross multiply and end up taking 80 divided by 20, so you get t equals 4 seconds. Now, how far downstream does the boat land? Well, downstream, in this particular case, if you look at what's happening in the question, means to the north, because the river is flowing north. So the question is, how far does the boat get pushed to the north? Well, we can use speed equals distance over time, or velocity equals displacement over time. But since we're talking how far north does it travel, we have to use the north velocity. Now the question becomes this: what do you use for the time? Well, we've already determined the time is 4 seconds, and I want to go back and show something to you. When I talked here about this boat, and I have these equations in red, I said the horizontal velocity is equal to the horizontal displacement over the time, and the vertical velocity is equal to the vertical displacement over the time. I didn't talk about the time in terms of direction, and that's because there is no direction with time. But these two times, this time and this time, are the same. These are the same. We can talk all we want about horizontal motion occurring independently of vertical motion and vice versa, but the fact of the matter is the boat does not travel 4 meters north, then 3 meters west, then 4 meters north, then 3 meters west. It's doing that at the same time. It really is traveling along that blue line. If you take a look, going back to t equals 0 seconds, there it is at t equals 0. It's traveling along this line continuously. So it travels at 4 meters per second and 3 meters per second at the same time. And that's why we are allowed, getting back to this question, that's why we are allowed to take this 4 seconds here and put it in our other equation. That's a little cloudy right now, so I hope that makes sense. What I'm saying is, if it's traveling across the river for 4 seconds, that means it will be traveling downstream for 4 seconds, so we can put that in. I've forgotten what the speed of the river is. The speed of the river is 5 meters per second, and it is north. So we can write 5 meters per second north. I'm not really sure I need to put the north in there. Equals the displacement, which we're trying to find, that's going to be north, over the 4 seconds. We can cross multiply there. 4 times 5 is 20 meters. So what happens here is the boat starts off looking across 80 meters of water, and the water is flowing to the north, and the boat is pointed east. The boat fires the engines. It ends up traveling east 80 meters in 4 seconds, so it lands on the other side of the river, but it's going to land 20 meters downstream from where it started. I hope that makes sense. Before I just answer number 3, again, I'm not in front of you, and my head's a little cloudy, as I said. I don't know what my pause time is like with this video. Part of me wants to say I'm going too fast, but I will post the link in our Google Classroom so that you could watch it again at your own leisure. And of course, the video can always be paused at any point for you to think about things. All right, now I'm going to introduce something that's going to become important as we move through Physics 20 and 30. And you may have already been shown this, but in examples 1 and 2, what is the physics principle used when working with the horizontal motion? So if we go back to example 1, example 1 was this situation. And the horizontal motion was essentially the boat moving towards the west at 3 meters per second. If you take a look at example 2, we have a boat that's moving, well, it's moving east at 5 meters per second. Pardon me. It's moving east at 20 meters per second. But the bottom line is both of those horizontal motions are uniform motion. And I think I started off on the very first day talking about what uniform motion is. Uniform motion means no acceleration. So horizontally speaking, there's no acceleration of the boat. What about the vertical motion? Well, the river in both of these was also moving with a constant speed, so this is uniform motion as well. Now, just to finish this off, we're done the lesson, but I want to talk briefly about a couple of things. If you were to go to your formula sheet and look under the physics principles section, what we've said, uniform motion, actually has a code on your formula sheet. The code is 0. And on an exam, you may be asked to record the physics principle in a numerical response question, and you would record the digit 0. All right, the other thing I wanted to mention is where we are going with this, and that's that in the last 2 lessons of this unit, what we are going to be looking at on Thursday of this week and Friday of this week, we're going to be looking at motion where one of these components is uniform motion and one of them is uniform acceleration, which is going to make things more challenging. I hope that that lesson went okay. Don't forget to check Google Classroom if you're looking for a link of the video. By my count, I suspect that you still have a fair amount of class time left. I'm thinking that this video is someplace between 30 and 40 minutes long, which means you have someplace between about 40 and 45 or 50 minutes left. And what you're working on for tomorrow are the 7 problems that are in your handout, and it looks like they are on page 36. You also have due tomorrow, which is tomorrow's Thursday, you also have due assignment number 1. I'm hoping to be back next week, but what you also need to be doing is for all of the lessons that you've been working on when I'm not there, you need to keep track of any assigned problems that you are having difficulty with or need me to go over when I return. And when I return, if we spend that first day just going over all of the material that was covered when I was away, that's fine. Anyway, I hope that you have a great rest of the class and a fantastic day. And I will talk to all of you through another video tomorrow. Take it easy.